How do we know how old the universe is? Why hasn't anyone sent a mission to the poles on Mars? And how far away can the supermassive black hole at the center of the Milky Way influence us? All this and more in this week's Question Show. It's time for the Question Show. Your questions, my answers. As always, wherever you are across my channel, if a question pops in your brain, just write it down. I'll gather them up and I will answer them here. Now, just let you know, I'm going to be off next week, but we're going to run another overtime questions episode, so everything will remain unchanged. All right, let's get into the questions. Smorrow. Could we ever work out exactly how many years old the universe is? Where exactly does the 13.77 billion years figure come in? Is there no way we could date all the hydrogen atoms that we have from the Big Bang? So this is a great question. And I think a lot of people gloss over the nitty-gritty details of how astronomers know the age of the universe. And so we're going to do a deepish dive into this. And so there are two main ways that astronomers know the age of the universe. The one way is to measure the redshift of objects that are moving away from us. And so we know that various galaxies at the farthest distances are moving away from us. And the farther away the galaxy is, the faster it is moving away from us. And the distances, essentially, or the speed that the universe is expanding, or the speed that the galaxies are receding, has been measured very accurately. And accurately to the point that then you could run the universe backwards and you could calculate when the things that are at the far left to you and the things that are at the far right to you were once in the same location. And that's how astronomers get the 13.7-ish billion years old for the age of the universe. And then there's a second way. And the second way is considered the gold standard, the one that is incredibly accurate. Although, I did interview Adam Rees, who Nobel Prize winner, one of the people who does the other work. But, and there is a tension between these two measurements. But, what we're going to go into is sort of why the measurement of the cosmic microwave background radiation is considered so accurate. So there has been this understanding of essentially the structure of the universe that's kind of been evolving over time. And the most modern understanding is that dark matter accounts for about 27% of the universe. Regular matter, the stuff that we're made of, is like 3%, and dark energy accounts for the rest. These measurements have been made through a bunch of ways, right? We've got gravitational lensing of galaxies. We've got to get at dark matter quantities. We've got measurements of type 1a supernovae to sort of figure out the acceleration of the expansion of the universe thanks to dark energy. And so astronomers have developed this model called the lambda CDM, the lambda cold dark model. And so based on all the observations, there is a way that dark matter tends to behave, and that matches this model. And so then astronomers have sort of taken that model and tried to sort of map it back to the very beginning of the universe, to really understand how the universe should evolve over time from the initial conditions of what we might see in the cosmic microwave background radiation to what we see as the structures today. And you get these sort of all these intervening periods that you can then sort of map out this evolution of the universe. And so with the Planck satellite, which is the sort of the most recent satellite that's designed to measure the fluctuations in the cosmic microwave background radiation, they were able to measure the precision. Essentially, they're measuring these temperature fluctuations in the CMB. And like the CMB is like 2.7 Kelvin, but it's like plus or minus these tiny little variations. And those variations map onto or are caused by changes in density in the beginning of the universe. And so with the observations made by the Planck satellite, they were able to measure these temperature variations and able to measure how far apart these various temperature fluctuations are in the CMB. And you get these sort of larger and larger patterns as you measure this. And so from those patterns, from those measurements, astronomers are then able to take that lambda CMD model, that model of the evolution of the universe, and then match it against the pattern that they're seeing in the cosmic microwave background radiation. And they were able to get like such a close accurate measurement of the CMB that they were then able to fit the sort of the model of the universe to get that early history, that early age of the universe. And they're actually able to get it within about 40 million years of uncertainty. In other words, they're certain, like the universe is 13.77 billion years old, plus or minus 40 million years. Like the measurement is incredibly accurate. And so you're not getting a direct measurement of the age of the universe. You're getting a model that very well describes the current state of the universe across all of the measurements that astronomers have made. And then the ramifications are that when you look into the CMB and you see the first version of what that will look like, you're then able to match that up. And that's how they get the estimate. Now, you can imagine sort of people have gone and said, well, couldn't we just measure the redshift of the cosmic microwave background and the way that we measure the redshift of galaxies that are speeding away from us? But the problem is that the cosmic microwave background radiation is this really sort of beautiful black body spectrum. It sort of gives off its photons in a very smooth way. When you compare that to a galaxy is going to have lots of stars, lots of lines in it that correspond to different kinds of chemicals. And you can really get a sense of what wavelengths of light were being given off by that galaxy. And then you can measure the redshift as you can measure how those wavelengths have changed around. The problem is the CMB, you don't get those really clear indications of the chemicals that are sort of being emitted, or the colors of the chemicals that are being emitted in the CMB. And so you just can't get a very accurate measurement, the redshift of the cosmic microwave background. So it wasn't until these first surveys of the cosmic microwave background to measure those temperature changes, they could finally start to figure out and compare the temperature, fit that into the model, and that gave them the age of the universe. Of course, the challenge is that the measurement made by the Planck instrument is different from the measurement that has been made by the people who are measuring the redshift of the galaxies. And so there is a discrepancy. This is the Hubble tension. And so people are trying to figure out, is it a problem with the measurement? Is it a problem with the measurement of the redshift? Is it a problem with the measurement of the CMB? Or is there like new physics to try and explain this? And all three are possibilities. I'm sure you noticed the Stargate planet name that appeared above my shoulder, and this is a way for you to vote, for you to tell us what you thought was the best question of the week. And the winner from last episode was from Christian Desalier. Do the different arms of the Milky Way come from different galaxy mergers? So thank you, everybody who voted on that. And the way you vote is that you're going to see a different Stargate planet name appear as I'm answering each one of the questions. And we'll also put a list in the timeline as well as down in the show notes. And then at the end of the episode, after you've like really thought about all of the questions and like carefully interrogated your thoughts and your feelings, then put the keyword down in the comments down below. And then you can ask a question, whatever, but we will count up all of those votes and we will celebrate it next week. Andre Ravenna 4435. Why don't we ever hear anyone talk about Mars ice poles? One would think it would be of great interest when looking for life, water, and other things of interest. We've never seen a mission to the poles. Why? Oh, we've seen a mission to the poles and it failed. So back in 1999, NASA launched a spacecraft called the Mars Polar Lander. And this spacecraft was designed to land at the South Pole of Mars. It was supposed to land in December of 1999. And so I had been doing my science journalism job for about 9 months by then. And the spacecraft entered the atmosphere and they never heard from it again. And they think that it crashed onto the surface of Mars and just hit too hard, litho-braked, as they say, and so it failed. Now, later on, NASA sent another mission called the Mars Phoenix Lander, which went to a similar location, but not right onto the poles, and was able to help give us these first understandings that there's a lot of water mixed in with the regolith at regions, not just to the pole. Like we know there are ice caps at the poles, but also the regolith that is away from the poles still has a lot of water mixed in with the Mars sand. And so, yeah, NASA had this exact plan. Let's send a mission to the poles of Mars. The mission crashed and they had to move on to the next mission. And so, you know, That's how this works. And like maybe someday someone will send a mission back, which would be great. And you're exactly right. There's a lot to be learned about the poles of Mars. And it's interesting, I've done plenty of interviews with people. And one of the interesting themes that I've heard from people is that, while we think about landing, say, humans near the equator on Mars, landing near the poles on Mars actually makes a lot more sense because, at the equator of Mars, you're going to get more sunlight. You're going to have warmer days and I guess slightly warmer nights than if you're at the pole, depending on what time of year you go. But there's no air and you're going to need to wear a spacesuit anyway when you're outside, and they have heaters. Like, people have been on the surface of the moon. It's cold. But if you go to the poles, then you have the water, and the water is the key to us being able to explore Mars, to be able to send rocket ships home with fuel that we've made locally on the planet. And so I wouldn't be surprised if, when people consider all of the possible landing sites for going to Mars, it's the poles where there is readily available water ice just sitting there on the ground that people can use to make their oxygen for breathing, water for drinking, grow plants with, and their fuel to be able to return home. Georgie on 2. What's the theoretical distance limit of the gravitational influence of the supermassive black hole in the center of the Milky Way? You are being affected gravitationally by every single thing in the observable universe. And so the answer to what is the gravitational influence of the supermassive black hole is really answered by the same question of what is the gravitational influence of everything that I can see, or everything where the photons of light can reach me, because gravity moves at the speed of light, and gravity can influence or can affect you for as far as the gravity has traveled. And so things that are 46 billion light years away from you in one direction, you are still experiencing the gravity. You are feeling the gravity of the cosmic microwave background radiation, even though there is not very much gravity. Like, be certain that these amounts are absolutely minuscule until you start to get to large objects like the Earth, the moon, the sun. Apart from that, you're really not feeling a lot of gravity, but you are feeling a little bit of gravity from the supermassive black hole, just because you're experiencing the gravity from everything. Now, people sort of think that there's something special about the gravity of a black hole, that it's like a vacuum cleaner that sucks in material, but it's just gravity like regular gravity. And so, if you took a black hole and with the mass of the sun, and you replaced the sun with the black hole, then all of the planets in the solar system would just continue to orbit this black hole sun in exactly the same way they did. Now, this thing would be tiny. It would probably be, a kilometer across, smaller. So it wouldn't be very big, but it would still have that amount of gravity. And so the solar system would just behave exactly the same. And so when you count up the mass of the supermassive black hole at the heart of the Milky Way, it's only about 1% of the mass of the entire Milky Way galaxy. People think it is the anchor, the heart, the important part for holding the Milky Way together. But no, if you just removed the supermassive black hole, Milky Way would go on exactly as it had before, except things would be a little different right down at the middle of the galaxy. And you could replace the supermassive black hole with a cluster of stars, 4 million stars buzzing around each other, and the rest of the galaxy would think that black hole was still there. Jameson 1776. Any thoughts on what the X-37B actually does? I know this is just speculation, if anything. So, we don't know exactly what the X-37B does. It is a Space Force classified mission, a space plane launched by Space Force every couple of years. And we don't exactly know what Space Force is using it for. But NASA has sent missions along on the X-37B, and we know what those are about. And so my intuition and kind of the reporting that I've done is that this is a way for Space Force to test out various hardware and technology in space. So imagine you develop a new optic system, you develop a new paint, you try to come up with some kind of radiation hardening for electronics, and you want to know what was the effect of that stuff that was in space for a long period of time. Well, you put it in the X-37B, you launch it off to space, you open up the bay doors on the space plane, and then you leave it exposed to the harsh reality of the cosmos for a couple of years, and then you bring it back and you see how it all performed. Did the electronics fry? Did the paint peel? And so that gives you a sense. And then Space Force can use what they've learned to incorporate that technology into their spy satellites and communication satellites and things like that. So, I don't think there's anything special about the X-37. It's a platform for testing out technology for Space Force. If you want to support the work we do at Universe Today, consider joining our Patreon club. Your support lets us have a minimum of ads and no sponsorship messages. Patrons get no ads on universetoday.com for life. Want the extra parts of the live stream that aren't in this edited version? You can sign up for a special patron-only podcast feed and get the overtime segments, as well as other special behind-the-scenes episodes, including our monthly patron-only question show. Thanks to everyone who has already subscribed, and welcome to our recent newcomers: Martin M., Eduardo, Roy Butler, Casey Ware, Edward Walton, Judy Fitzpatrick, OICU 812, Edward C. Ratledge, Nuno Abreu, Pete Hall, and Dean Fugate. Join the club at patreon.com/universe today. Hondo, why not abandon the SLS and cut our losses since we have Starship? Why even want a Mars sample return mission? We are sending people there just as soon. So maybe you know something about Starship that I don't, but from my impression, we don't have Starship. From what I can recall with the Flight 4 was you got the Super Heavy landing in the Gulf of Mexico and sinking to the bottom. You got Starship landing in the Indian Ocean and sinking to the bottom. We got some problems with the heat tiles for the Starship. And now we're waiting for flight number 5. And hopefully they will have solved a bunch of those problems. But we are a long way away from that being a sort of human rated, approved launch vehicle capable of taking off from Earth and sending astronauts to the moon. But NASA has already incorporated the human landing system, the Starship that's designed to land on the moon, into their plans for Artemis. In 2026, the plan is that the NASA astronauts are going to get into the Space Launch System that's already built, right? It's already built, it already exists. And they're going to get into the Orion capsule. They're going to fly to the moon. They're going to meet up with Starship, that thing you talked about, and they're going to move over into the Starship. Starship's going to take them down to the surface of the moon. They're going to get out. They're going to do some science. They're going to get back in to Starship. It's going to fly them back up to lunar orbit, and then they're going to get back into the Orion capsule. And the Orion capsule has already been tested a couple of times, including a flight all the way out and around the moon. So we know that works. And then they're going to be able to come home. And so what else do you want, right? Like, they are incorporating Starship into the return to the moon in a very fundamental way. The Starship is being depended upon to get them down to the surface of the moon and back up into orbit, in a sort of reusable manner. And that feels like a really important first step. Sure, if SpaceX wants to demonstrate that you don't need the whole SLS thing, Orion capsule thing, any of that stuff, and they can just send a launch directly to the moon and land on the moon and then come back home safely, re-enter the Earth's atmosphere with humans on board, and land safely at the Mexilla in Boca Chica, that's a tall order. And so I don't think we're anywhere close to that. And yet Congress has demanded. Like, remember, this isn't like NASA going like, oh, we should just go to the moon. Like, that sounds good, guys. Yeah, let's do that. No, President Trump decided they were going to go to the moon. And then Congress approved the bill and then gave them the money and defined their contractors and told them what the plan is. And NASA's job is to implement the plan. And so, yeah, by all means, when there is a more flight-proven stack, then you can see people actually going to the moon on Starship. But there's like a whole bunch of tests. Like, I know people think it's just around the corner. I am skeptical that it's going to come together probably within the next decade or so. And so the question is, like, do you put your space exploration plans on hold and wait for Elon Musk and SpaceX to develop the technology and make it safe and continue forward? So, this is like a FOMO question, the fear of missing out, that in the software industry, people come up with various kinds of technology, or they say they're going to come up with technology, and that makes people like not invest in that technology, waiting to see how it turns out. And so right now we're kind of stuck in this limbo. Starship is making incredible progress. We've seen a bunch of tests. On paper, it's a really exciting launch platform, but it doesn't exist yet. It doesn't do its job yet. And so will we wait for them to figure out all the problems, or is it better to have multiple irons in the fire, try and come up with different ideas at the same time, and then when one of them pans out, when competition sort of works in your favor and you actually get that flight to the moon? And then the same thing goes for Mars. Like, yeah, if SpaceX can demonstrate that they can send a Starship to Mars, land on the surface, refuel out of local resources, deploy rovers and landers that can grab samples, bring them back to Starship, refuel itself, and then take off from the surface of Mars and return safely to Earth and get back through the Earth's atmosphere, then that would be wonderful. But like, that is like a 3-year, maybe an 18-month test to just demonstrate that you can do that. And you're going to have the inevitable issues and challenges that come with that. So right now we are in this weird place. Well, there's multiple people trying out multiple ideas. There's everything that SpaceX is trying to do, but then there's their existing flight hardware as well, like Falcon Heavy. Falcon Heavy could send a Mars sample return mission. There's what NASA's doing with Space Launch System. There's other providers, and there's what the Chinese are doing. So I think it's better to remain flexible, better to sort of move forward and not just put all your eggs in one basket. Oscar Polya, what is the evidence we need to find out if the universe is finite or infinite? Right, so we don't know whether we live in an infinite universe or a finite universe. And so like an infinite universe is pretty weird. You imagine that you could move in any one direction forever and never return to your starting point. Imagine if you set out on the surface of planet Earth and you just started walking and you never returned to your starting point. That would be very peculiar. Or maybe that's what you'd expect. And now we know that in fact it's a ball and you return to your starting point. So that's weird. And then the other possibility is that the universe is finite. And that is also weird, because if you went in one direction long enough, you would return to your starting point. That if you could see forward infinitely far, then you would see your backside. And so we don't know which one it is. And that is because when we measure the curvature of the universe, back to that analogy of the curvature of the Earth, we can't tell whether it just goes on forever or whether there is a finite curvature that then brings you back to your starting point. And we know that the real universe, the actual universe, is way bigger than the universe that we can see, like thousands of times more volume than what we perceive in our observable universe. But that's a minimum. In other words, you measure the curvature of the universe, and to your very best, like the point where your measurements would no longer tell you, the very minimum, that is thousands of times bigger than the observable universe that we see today. And so if the universe were smaller than that, we could actually measure that curvature of the universe and know how big the actual universe is outside of the observable universe that we can see. So we may never know. We're going to continue to try to measure the curvature of the universe more and more carefully, but eventually you're just going to get to a practical limit that you can't measure anymore. And if the universe continues to feel like it's flat, then you will still not know. You'll never know whether it's infinite or finite, just you'll know the bottom end of your estimate. Hina Mtiaz, please talk about the Europa Clipper mission. I'm very excited. So the Europa Clipper mission, this is a mission by NASA that's going to be going to Europa, which is one of the Galilean moons, the ones discovered by Galileo. And Europa is the second closest moon to Jupiter. Io's the closest, and then you've got Ganymede and Callisto. And what makes Europa really exciting is that we can see from the surface of the moon, it's very young. It appears to be refreshed on a regular basis. And in fact, you can see what looks like cracks. And so astronomers think that in fact, there is a vast ocean of water underneath the ice, underneath a thick shell of ice on Europa. And this is really exciting because you've got liquid water on a place that is not Earth. And where we find water on Earth, we find life. And so is there life on Europa? Well, we kind of need to know more about this moon. And so that is the goal of the Europa Clipper. The mission is due to launch in really just a couple of weeks, theoretically. And it's going to take a few years to get to Jupiter. Typically, the flight out there is about 5 years. And when it gets out to Jupiter, it's going to go into this very long flyby around Europa. So it's going to be doing this long elliptical flight where it goes out pretty far out and then flies in, does a really close flyby, and then goes back out. And the reason they're doing this is because the radiation environment close to Jupiter is quite intense. And so you want to spend as little time as possible in that intense radiation region before you fly back out into farther away from Jupiter. And Europa Clipper has sort of the standard suite of scientific experiments on board. It's got cameras, it's got transmitters, it's going to be able to measure the chemistry of the surface of Europa. But what it has that's special is it has a ground penetrating radar system. It has the ability to scan below the surface of Europa. Hopefully, if everything goes well, it can actually see all the way down through the ice to measure the depth of the ice and figure out where the water begins on Europa. But in addition to that, it should be able to find pockets of water, of liquid water that are trapped under the ice. It could well be that, because Europa has this tidal flexing from Jupiter, it has a lot of heat that is escaping out of the moon, and it is sort of liquefying, melting some of this water ice at various pockets at various levels. And so hopefully from Europa Clipper, we will get a really detailed scan of the surface of the moon. We're going to get sort of a measurement of the structure under the surface to know where the pockets of ice are in water and what is the depth of the ice shell itself. And the hope is that we will see geysers. We know that there are geysers on Enceladus. There are probably geysers on Triton. And this is a place where the water in that ocean underneath the ice is making its way through and out into space. And this is the perfect place to be able to grab a sample. There are hints that there are these geysers on Europa, but we just don't know for sure. And so with the Europa Clipper, we should get really good detailed images within a few hundred kilometers of distance from the surface of the moon. We should really kind of nail down what those parameters are. So, Europa Clipper is a way to really well understand this moon and is sort of the next stage. Next come the landers, next come the rovers. And ideally, some future mission will attempt to melt down through the ice shell to reach the liquid ocean beneath and try to search for the evidence of life in the ocean on Europa. Josh Schultz, since the Starlinks have become a problem, are you hopeful that the eventuality of Starship will allow cheap, gigantic telescopes to be placed into orbit much more affordably, thereby negating the effects of the Starlinks? I think that we hope that Starship will be capable of launching giant telescopes and will be able to do so relatively inexpensively. Like when you think about the cost of building a telescope and then launching it, the launch costs typically run about half the cost of your mission. So if you're going to build a $1 billion mission, you're going to set aside about half your money, $400 million for your launch provider. But if Starship comes online, then maybe it can drop those costs down and maybe you only spend $40 million for your launch. And so the savings go into constructing your mission. But also because Starship is so powerful, can launch 100 tons into low Earth orbit, and it could probably launch, more than any other launch provider out to geostationary orbit or out to L2, then you have a lot more flexibility, both in the size of the spacecraft that you're going to put into it, as well as the weight. You're not so constrained in either of those things, and that's really exciting. But there are plenty of benefits for having a ground-based telescope, like the upcoming extremely large telescope, a 39-meter telescope that's being built in Chile. It has a very well-built adaptive optics system that's going to allow it to ignore the effects of the Earth's atmosphere. It's going to be able to see Earth-sized worlds orbiting around sun-like stars, and it's going to be more powerful than James Webb will be. And we would be hard pressed to launch a 39-meter telescope out into space. It would be amazing if we could, but we're still a couple of years away from being able to do that. And yet the construction cost for building the extremely large telescope is a tenth the price of James Webb. So there's real benefit to having ground-based observatories. Plus they're upgradable. You can go in and you can swap out the instruments on it. You can put in new instruments. You can adapt the facility as we learn more about the universe, put on, new optic systems, and just sort of continue to upgrade them. When you think about some of the most productive observatories in the world, things like the Keck interferometers, the Gemini North and South, the Very Large Telescope, these have been just hard-working observatories that have actually contributed most of the science that we have in astronomy. And so we want to be able to have our cake and eat it too. We want to be able to have ground-based observatories that can continue doing that work, and we want to be able to have space-based observatories. And yeah, I think, if Elon Musk said, sorry about Starlink, we're going to launch a space telescope that perfectly matches the capabilities of every single telescope on Earth for free, I think the astronomy community would be grateful and they would love to see that, but we're not seeing that. And we won't expect to see that. We're going to see a launch platform that future missions can go on at a fraction of the price of current missions, but we're also going to see the downsides. We're going to see radio astronomy hampered by Starlinks. We're going to see visual astronomy hampered by Starlinks, especially things like Vera Rubin and the kinds of telescopes that are scanning the horizon for dangerous near-Earth asteroids. And this could have been much less of a problem if we'd had more communication, if people had defined corridors where satellites shouldn't go, that you provide accurate timing to the observatory so they can do their observations at the right times. I think there is a way that the astronomical community and the satellite community can work together, but those conversations never happened. And so we just went straight to constellation, and now astronomers are having to sort of work within the existing regulation and the existing infrastructure to try and advocate for the science. And it's not going so well. Biggles Tintin, how often does the Earth capture another moon? So the time that you're watching this, the Earth has recently captured a tiny little moon and is going to keep it in our orbit for a couple of months. And so the thing is not actually a moon. They call it like a temporary satellite. And so it just means that it's going to go in this sort of weird horseshoe-shaped orbit around the Earth and remain relatively close to us, and then it's going to spin back out and go into orbit around the sun again, gone forever. And this has happened many times. So you actually can see over the last, say, 100 years, there's been a couple of dozen times when the Earth has gotten a temporary moon, a quasi-satellite. So this happens on a regular basis, and these things are small. I mean, this thing is, 10 meters across, very tiny. And so, because they're so small, the interactions between the Earth and the moon and the gravitation sort of field between both creates a very unstable environment. So these things can't go into orbit around the Earth in the way that the moon does. So this happens regularly. And we also have asteroids that are in a resonance with the Earth. And so they get close to the Earth on a regular basis as both the Earth and this asteroid are going around the sun. But they're not really moons. So the Earth only has one moon. All right, those are all the questions that we had this week. Thank you, everyone who put in your questions, both in the YouTube comments as well as the people who came for the live show. We do the show every Monday at 5 p.m. Pacific time, where you can come ask your questions, banter with other people in the chat and with me, and it's a lot of fun. And it is 2 hours long, and so what you're seeing is the edited down version of the first half, but the full question show is 2 hours long. And you can get a link to the entire unedited live stream to get all of the bloopers and the flubs and the secrets that are revealed. If you follow us for free on patreon.com/universetoday, once you follow, then you'll get a link to each episode of the question show, and we include a link to the actual unedited live stream. So check that out. All right. Now I'm going to talk about a very disruptive technology, but first I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew Gross, Barry Lake Roofing, David Gilton, and David Matz, Dennis Alberti, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Paul Rohrbach, ScienceWorldRecord.org, SpiderSwap.io, Stephen Krasaki, Stephen Fowler-Munley, and Vlad Chiplin, who support us at the Master of the Universe level. And all our patrons. All your support means the universe to us. So I've been testing out a new piece of technology that is so profound that I think I just need to talk about this. And this is the Notebook LM that has come from Google. And on the surface, this is a way to do research projects. So you can put in a bunch of documents that you're working on like if you're working on a specific article, or you're writing a book or whatever, and you can just put it all into one place. And then you can interrogate the documents. And so you can ask questions about it. And so I'll give you an example. We're going to work on a series of episodes where I talk about sort of the moments that I learned new things about James Webb or new things about the cosmos or whatever, based on the interviews that I've done, the reporting that I've done with various guests. And, it's like needle in a haystack type work. And so we're going to be able to go and dig through a series of interviews on a topic and find individual little quotes out of those. This is all done by the Notebook LM. So if you're like a writer, you're a researcher, and you want to sort of use an AI assistant to do this, I highly recommend checking this out. But the creepy part is the podcast. And so you can generate an audio podcast of the research material, no matter how obscure it is. And so like I had it generate a podcast based on land zoning in my area of British Columbia. You can have it analyze your credit card statement, or you can take a really tricky piece of research and have it be able to analyze it and do a podcast. And the podcast is good. Like it is two hosts bantering. They sound lifelike. They make jokes. They are providing what seems to be fairly accurate information about my credit card statement or land zoning use in British Columbia. And like we're 2 years really into this revolution of large language models and the transformer model being used to do this kind of thing. And it's crazy. It's scary. It's weird. It's bizarre. It's cool. So anyway, that's it. I have no, you can decide what you think are the consequences of this. But my mind is blown. And I highly recommend generate a podcast over something that's super nerdy that you're into, that's really obscure. And I think you'll find it, or something that you're having trouble understanding. And my guess is you will get something that you can understand and are entertained by. And who knew? My days are numbered at this point. All right. We'll see you next week.